In this lecture video, we're going to look at the general procedure for fitting a structural equation model. This is done by estimating the parameters in the model. In order to understand this estimation process, we need to first understand how the SEM induces structure on the covariance matrix of the manifest variables, and where the various parameters in the model show up in that induced covariance structure. This induced structure is the key to the estimation process. Here's an outline of what we'll be looking at in this video. In order to do this, we need to have a context, and that context will be a confirmatory factor analysis model. So we'll introduce that context, and then we'll look at the covariance matrix for this model. We'll look at it in two ways. We'll first look at it as a raw unstructured covariance matrix, and then we'll derive the model-implied or structured covariance matrix that corresponds to the model. And then finally, we'll discuss the procedure for fitting the structural equation model. So let's take a look. So let's first describe the context that we'll be working in, a confirmatory factor analysis model. Consider a generic confirmatory factor analysis model consisting of three latent constructs, which we will denote by F1, F2, and F3. It's proposed that three manifest variables are indicators of the latent construct F1, three manifest variables are indicators of the latent construct F2, and three manifest variables are indicators of the latent construct F3. So here is the path diagram for this confirmatory factor analysis model. We have three ovals for the three latent constructs, F1, F2, and F3. Between each pair of latent constructs, we have two-way arrows, and so we see that we are allowing the latent constructs to be correlated. We have 9 squares representing the 9 manifest variables. The squares for V1, V2, and V3 have one-way arrows coming into them from latent construct F1. The 3 squares for V4, V5, and V6 have one-way arrows coming into them from latent construct F2. And then finally, the squares for manifest variables V7, V8, and V9 have one-way arrows coming into them from latent construct F3. In addition, each of the manifest variables has a one-way arrow coming into it from its own error term. Those error terms labeled E1 through E9. And you'll recall that we identify parameters to be estimated in the model using asterisks. Now here is the representation of the confirmatory factor analysis model using statistical and mathematical notation. And so we see that V1 is equal to lambda 1 times F1 plus E1. V2 is lambda 2 times F1 plus E2. V3 is equal to lambda 3 times F1 plus E3, and so on. In addition to the regression type of equations, we also need to specify equations describing assumed relationships between error terms, between factors, and between the factors and the error terms. In the first bullet point, we see that we are setting the covariance between each pair of error terms equal to 0. And so we are not allowing the error terms to be correlated. In the second bullet point, we are assigning notation to the variances of the individual error terms, theta I being the variance of error term I. In the third bullet point, we see that we are setting the covariance between each latent construct and each error term equal to 0. And so we are not allowing the factors and the error terms to be correlated. In the fourth bullet point, we are assigning notation for the covariance between pairs of latent constructs. And then finally, in the fifth bullet point, you'll see that we are setting the variance of each latent construct equal to 1. So using the approach that we used in a previous example where we looked at a confirmatory factor analysis model, we see that we have a number of parameters that need to be estimated. we have the 9 loadings, lambda I going from 1 to 9. We have 9 variances of error terms, theta 1 through theta 9. And we have 3 parameters for the covariances between pairs of factors. So cap phi 1, 2, which is the covariance between F1 and F2, cap phi 1, 3, which is the covariance between F1 and F3, and cap phi 2, 3, which is the covariance of F2 and F3. And so based on this counting, we have 21 parameters that will need to be estimated in order to fit this SEM. Now let's take a look at what we can do to help ensure that the model that we have specified is identifiable. Raykov in 2000 gave 6 rules for determining which components in an SEM are model parameters in order to help ensure that the model is identifiable. These rules are given on the following slides. Now keep in mind that these guidelines can help increase the likelihood but cannot guarantee that a structural equation model will be identifiable. Rule 1 is that all variances of independent variables are model parameters. And so let's take a look at the path diagram. For the purpose of identifying variances and thinking about the independent variables, the error terms are considered to be independent variables because they have one-way arrows going from them into the manifest variables. And so you can see that we have an asterisk on each of the error terms, E1 through E9, and those represent the variances of those error terms. Now, from this vantage point, the latent constructs, F1, F2, and F3, because we have one-way arrows emanating from each one of those to their corresponding indicators, they are independent variables as well. And so based on Rule 1, we would conclude that each of these factors has a variance associated with it that is a parameter that needs to be estimated. And so I've included those asterisks here with the red squares around them to help show where those are. Now we're going to see that a subsequent rule is going to reverse that part of the counting of the parameters. Rule number 2, all covariances between independent variables are model parameters. So again, looking at the path diagram for our confirmatory factor analysis model, we see that we have 3 asterisks in the path diagram corresponding to those covariances between the pairs of latent constructs. Rule number 3, all factor loadings connecting the latent variables with their indicators are model parameters. Looking at the path diagram, we see that we have lambda 1 through lambda 9, the factor loadings. Each one has an asterisk associated with it, and so we have identified those as parameters that need to be estimated in order to fit the model. All regression coefficients between observed variables or latent constructs are model parameters, and we don't have any of those in this model, so we won't look at the path diagram. Rule number 5, the variances and covariances between dependent variables and the covariances between dependent variables and independent variables are never model parameters. And again, we have none of those in this model, and so we don't need to go look at the path diagram. And then finally, Rule 6. For each latent construct included in a model, the metric of its scale, that is, its standard deviation or variance, needs to be set to a particular value. And so referring back to a previous slide, the 5th bullet point on this particular slide, we saw that we were setting the variance of each of the latent constructs, F1, F2, and F3, to be equal to 1. And so this is the rule that is going to override Rule 1, which said that the variances of all independent variables are parameters that need to be estimated. This supersedes that rule, and so these asterisks become 1, and so they don't need to be estimated, and so we can remove them from the path diagram. So again, Rule 6 overrides Rule 1 when an independent variable is a latent construct. And so again, reviewing our list of parameters that need to be estimated, we have 9 loadings, we have 9 variances of error terms, and we have 3 covariance parameters. And so we have correctly identified the 21 parameters that need to be estimated in order to fit this structural equation model. Now, what are necessary conditions for these parameters to be identifiable? Well, again, the number of parameters must be no more than the number of non-redundant entries in the covariance matrix of the manifest variables. How many non-redundant entries in the covariance matrix of the manifest variables are there? We're going to get there, but see if you can figure that out before we do. In addition, what conditions will lead to the estimators being reliable? What does it mean for an estimator to be reliable? This will be a topic for another lecture video. So let's look at the covariance matrix. And let's first look at the raw, unstructured covariance matrix. We have 9 manifest variables, V1 through V9. And so the covariance matrix for the vector of manifest variables is a 9 by 9 covariance matrix. Here we're going to represent the entries in the covariance matrix by sigma sub ij, where I corresponds to the row and j corresponds to the column. Now let's remind ourselves what the entries in the covariance matrix cap sig represent. Let bold V be the 9 by 1 vector containing the 9 manifest variables V1, V2, and so forth up to V9. Then cap sig, the covariance matrix of bold V, is a 9 by 9 matrix. For each I going from 1 to 9 and j going from 1 to 9, the ij entry of cap sig, denoted by sigma sub ij, is the covariance of V sub I and V sub j. Now this fact, combined with the covariance property 3, implies that the II entry, that is the ith diagonal entry of the covariance matrix cap sig, and this entry is denoted by sigma sub ii, is equal to the variance of the ith manifest variable. In addition, sigma sub ij, which by definition is the covariance of V sub I and V sub j, by covariance property 2 is equal to covariance of V sub j and V sub I, and that by definition is sigma sub ji. And so sigma ij is equal to sigma ji, and this implies that cap sig is a symmetric matrix. Now because of this, when displaying the entries in cap sig, it suffices to show just the entries on the diagonal and those below the diagonal, that is the lower triangular portion, or the entries on the diagonal and those above the diagonal, that is the upper triangular portion. This will be helpful to save space when writing it out. The next slide shows the lower triangular portion of cap sig. Next, let's look at the model-implied covariance matrix. Note that the number of unique, that is non-redundant entries in the 9 by 9 covariance matrix cap sig is given by p times p plus 1 over 2, or in this case 9 times 10 over 2, which is 45, where p is the number of manifest variables and therefore the dimension of the covariance matrix. These non-redundant entries are represented by the lower triangular portion of the covariance matrix cap sig as shown on the next slide. Because the covariance matrix is symmetric, once we have expressions for these entries, the expressions for all entries in the covariance matrix will be known. And so here is the lower triangular portion of that covariance matrix. So we're going to derive formulas, derive expressions for each of these entries in the covariance matrix. Let's start off with the diagonal values. In general, for I going from 1 to 9, sigma sub I is equal to the covariance of V sub I and V sub I, or the covariance of V sub I with itself, and that, you'll recall, is the variance of V sub I. This result follows by application of covariance property 3. Now, for I going from 1 to 3, the variance of V sub I is equal to the variance of lambda sub I times F1 plus E sub I. Now that is equal to lambda sub I squared times the variance of F1 plus the variance of E sub I, and that turns out to be lambda squared times 1, where the 1 is the variance of F1, plus theta sub I, and so the variance of V sub I is equal to lambda sub I squared plus theta sub I. For I going from 4 to 6, the variance of V sub I is equal to the variance of lambda sub I times F2 plus E sub I. That is equal to lambda sub I squared times the variance of F2 plus the variance of E sub I. That is equal to lambda I squared times 1, where again 1 is the variance of F2, and then plus theta sub I. And that simplifies to lambda I squared plus theta I. And then finally, for I going from 7 to 9, the variance of V sub I is equal to the variance of lambda sub I times F3 plus E sub I. That is equal to lambda sub I squared times the variance of F3 plus the variance of EI. That is equal to lambda I squared times 1, where the 1 is the variance of F3, and then plus theta sub I. And so that simplifies to theta sub I squared plus theta I. Now these results follow by application of covariance property 5. Note that in each of these three cases, the expression is the same. Therefore, for I going from 1 to 9, the ith diagonal entry of cap sig, which again is the variance of the ith manifest variable, is given by lambda I squared plus theta I. So this accounts for the 9 diagonal entries of cap sig. Now let's work on the off-diagonal elements of the covariance matrix. Now for I going from 1 to 3 and j going from 1 to 3, where I is different than j, sigma sub ij, which by definition is the covariance of v sub I and v sub j, is equal to the covariance of lambda sub I times f1 plus e sub I with lambda sub j times f1 plus e sub j. This is equal to lambda I times lambda j times the covariance of f1 and f1 plus lambda I times 1 times the covariance of f1 and ej plus 1 times lambda j times the covariance of e sub I and f1 plus 1 times the covariance of e sub I and e sub j. This in turn is equal to lambda sub I times lambda sub j times 1, because the covariance of f1 and f1 is the variance of f1, and we know that that's equal to 1. And the rest of the other terms are equal to 0 by the assumptions we've made about the model. And so sigma sub ij is equal to lambda sub I times lambda sub j, which is also equal to lambda sub j times lambda sub I. So these results follow by application of covariance properties 2 and 4, and it accounts for 3 entries in the lower triangular portion of cap sig, as shown on the next slide. So those results provide the formulas shown here. Next, let's consider I going from 1 to 3 and j going from 4 to 6. So in this case, sigma sub ij is equal to the covariance of v sub I and v sub j, which turns out to be equal to the covariance of lambda sub I times f1 plus e sub I with lambda sub j times f2 plus e sub j. This is equal to lambda sub I times lambda sub j times the covariance of f1 and f2 plus lambda sub I times 1 times the covariance of f1 and ej plus 1 times lambda j times the covariance of e sub I and f sub 2 plus 1 times the covariance of e sub I and e sub j. Now this is equal to lambda sub I times lambda sub j times cap phi sub 1, 2, because cap phi sub 1, 2 is the notation that we're using for the covariance of f1 and f2. And all of the other terms are 0 because the covariances of the latent constructs with the error terms and the covariances between different error terms are all equal to 0 by assumption. And so sigma sub ij is equal to lambda sub I times lambda sub j times cap phi sub 1, 2, and that's also equal to lambda sub I times lambda sub j times cap phi sub 2, 1. This result follows by application of properties, covariance properties 2 and 4, and it accounts for 9 entries in the lower triangular portion of cap sig, as shown here. Continuing on, we'll again let I range from 1 to 3, and in this case, j is going to go from 7 to 9. So in this case, sigma sub ij, which is the covariance of v sub I and v sub j, is equal to the covariance of lambda sub I times f1 plus e sub I with lambda sub j times f3 plus e sub j. Now this is equal to lambda sub I times lambda sub j times the covariance of f1 with f3 plus lambda I times 1 plus the covariance of f1 with ej plus 1 times lambda sub j times the covariance of e sub I with f3 plus 1 times the covariance of e sub I with e sub j. This is equal to lambda sub I times lambda sub j times cap phi sub 1, 3, with the rest of the terms being 0 because of the assumptions about the covariances. So this is equal to lambda sub I times lambda sub j times cap phi sub 1, 3, which is also equal to lambda sub I times lambda sub j times cap phi sub 3, 1. Again, this result follows by application of covariance properties 2 and 4, and it too accounts for 9 entries in the lower triangular portion of cap sig, as shown here. So we're making steady progress. Next, let's let I range from 4 to 6 and j range from 4 to 6 as well, where I is different than j. In this case, sigma sub ij is equal to the covariance of v sub I and v sub j, which is the covariance of lambda sub I times f2 plus e sub I with lambda sub j times f2 plus e sub j. This is equal to lambda sub I times lambda sub j times the covariance of f2 and f2 plus lambda I times 1 times the covariance of f2 and e sub j plus 1 times lambda j times the covariance of e sub I and f2 plus 1 times the covariance of e sub I and e sub j. This simplifies to lambda I times lambda j times 1, where again 1 is the covariance of f2 with itself, which is the variance of f2 and has been set to 1. And the rest of the terms are equal to 0 because of the assumptions about the various covariances in those terms. So this is equal to lambda I times lambda j, which is also equal to lambda j times lambda I. This result follows by application of covariance properties 2 and 4, and it accounts for the 3 entries in the lower triangular portion of cap sig as shown on this slide. Next, let I range from 4 to 6, while j ranges from 7 to 9. In this case, sigma sub ij, which again by definition is the covariance of v sub I and v sub j, is equal to the covariance of lambda sub I times f2 plus e sub I with lambda sub j times f3 plus e sub j. This in turn turns out to be equal to lambda I times lambda j times the covariance of f2 with f3 plus lambda I times 1 times the covariance of f2 with ej plus 1 times lambda j times the covariance of e sub I with f3 plus 1 times 1 times the covariance of ei and ej. This is equal to lambda I times lambda j times cap phi sub 2, 3, where cap sig sub 2, 3 is the notation that we're using to represent the covariance of f2 with f3. And the rest of the terms in the sum are equal to 0, again because of the assumptions made about the various covariances that are represented in those terms. And so this simplifies to lambda I times lambda j times cap sig sub 2, 3. And this is equal to lambda I times lambda j times cap sig sub 3, 2. This result follows by application of covariance properties 2 and 4, and it accounts for 9 entries in the lower triangular portion of cap sig as shown on this slide. Next, let I range from 7 to 9 and j range from 7 to 9, where I is different than j. And so sigma sub ij, which by definition is the covariance of v sub I and v sub j, in this case is equal to the covariance of lambda sub I times f3 plus e sub I with lambda sub j times f3 plus e sub j. This is equal to lambda I times lambda j times the covariance of f3 with itself plus lambda I times 1 times the covariance of f3 with e sub j plus 1 times lambda j times the covariance of e sub I with f3 plus 1 times 1 times the covariance of e sub I and e sub j. This simplifies to lambda sub I times lambda sub j times 1, where again 1 is the variance of f3, which is the same as the covariance of f3 with itself. And then the rest of the terms are equal to 0 because of the assumptions made about the covariances in those terms. So the sigma sub ij is equal to lambda sub I times lambda sub j, which also can be written as lambda j times lambda I. This result follows by application of covariance properties 2 and 4 and accounts for 3 entries in the lower triangular portion of cap sig as shown on this slide. So this is the full model-implied covariance matrix that is induced by the structural equation model that we have, this confirmatory factor analysis model with 3 factors and 9 manifest variables, 3 manifest variables being indicators of each of the 3 latent constructs. All of the parameters in that model are showing up in this model-implied covariance matrix, and this is very important. This model-implied covariance matrix is the key to estimating the parameters in this model. In addition to the model-implied covariance matrix, we have the raw covariance matrix or unstructured covariance matrix, and the estimator of that raw unstructured covariance matrix is the sample covariance matrix. And so we're going to be utilizing both the model-implied covariance matrix and the sample covariance matrix when we estimate the parameters in the model to fit the SEM. And so let's look at the procedure now for fitting an SEM. To do this, we first need to think about the different kind of variables that we have in the model. These are categorized as free variables, fixed variables, and constrained variables. In order to fit a structural equation model, each model parameter must be identified as being one of the following three types: either a free parameter, a fixed parameter, or a constrained parameter. Let's first talk about free model parameters. The parameters determined by the 6 rules are commonly called free parameters. Free parameters can vary freely over the parameter space without constraint. Next, we'll talk about fixed model parameters. These are parameters that have their value set at a fixed constant. And finally, constrained model parameters can vary, but they must do so in some relation to other variables. For example, they must be equal to other variables. And so we now have a model-implied covariance matrix, cap sig, and we have a sample covariance matrix, which we'll denote by S. And so we have our model-implied covariance matrix with the expressions that we derived previously. And then we have our sample covariance matrix, which is our estimator for the raw unstructured covariance matrix. And so you can see here that I have put hats on the sigmas in the matrix. And so if we had real data, then we would have actual values in the entries for this sample covariance matrix. So let sigma hat denote an estimator of the model-implied covariance matrix cap sig possessing the same structure. And so to do this, we will not only put a hat on the cap sig, but we're going to put hats on all of the parameters in the expressions for that model-implied covariance matrix. We fit the structural equation model by finding the estimator of the model-implied covariance matrix, cap sig hat, that is as close as possible to the observed sample covariance matrix, S, according to some criterion. A criterion function that gives a distance between cap sig hat and S is called a fit function and will be denoted by F, perhaps with a subscript to identify the type of fit function being used. There are several types of fit functions commonly used in structural equation modeling. Here are the fit functions that are commonly used. Unweighted least squares, and so we will subscript the criterion function f with ULS, and this is the sum of the squared differences between corresponding elements of cap sig and S. The three fit functions below are similar to the unweighted least squares criterion function, but they differ in that they compute a weighted sum of squares according to their own set of weights. And so maximum likelihood is a common criterion. Generalized least squares is another criterion commonly used. And then finally, asymptotic distribution free or weighted least squares is also used. Maximum likelihood and generalized least squares can be used when the data are normally distributed or nearly so. On the other hand, asymptotic distribution free should be used when the data are seriously non-normal. Now, to use asymptotic distribution free, the sample size needs to be large, and a cautious rule of thumb is that there need to be more than 10 times the number of free model parameters in terms of the number of observations. Now let's go back and talk about the identifiability of the SEM. So we pose the question, what are necessary conditions for these parameters to be identifiable? We know that the number of parameters, which in this case is 21, must be no more than the number of non-redundant entries in the covariance matrix of the manifest variables. How many non-redundant entries in the covariance matrix of the manifest variables are there? Well, there are 9 times 10 over 2, or 45, non-redundant entries in the covariance matrix of the manifest variables. And so this criterion is satisfied. What can we conclude from this about the identifiability of the model? Well, using this criterion alone, because 21 is no more than 45, all we can conclude is that the model may be identifiable, but this does, in and of itself does not prove that the model is identifiable. But when combined with the fact that we have followed the 6 rules for identifying parameters to be estimated, we can have a fair amount of confidence that the model is in fact identifiable. So that's what I wanted to show you in this lecture video. I'll see you in the next lecture video.